that is magnetism and electromagnetism. It will be going to the first lecture of this, and we'll be doing three lectures on this unit, covering each chapter in one lecture.
Mhm.
So in today's class, we'll be talking about and how it originates, how it got discovered, and we will talk about magnetism, like all those phenomena associated with the magnetic field. So
Mhm.
it arises due to moving charges, as we already know. So if you remember, when we talked about charge, we said if the charge is in motion, it produces magnetic. Again, it is a vector quantity.
Mhm.
So if some charge is moving with certain velocity, there is a special kind of field which originates due to this charge, due to the motion of this charge, and that field we called magnetic field. Just like electric field, magnetic field is also there, and because of this magnetic field, we see various phenomena around us.
Mhm.
So if we talk about a bar magnet and try to understand that how field actually originates from it. So first of all, we need to understand that bar magnet is something which has two poles. One is north pole and the another is south pole. North pole is the part of the magnet from where field originates, whereas south pole is the part of the magnet at which field terminates.
Mhm.
This is the situation which is going on outside the bar magnet, but inside the field is aligned from south to north. So always remember the direction of field. Outside the bar magnet, it is north to south,
Mhm.
but inside the bar magnet, it is from south to north.
Mhm.
So there are two images. The one is representing a bar magnet, and the other is representing a solenoid. Solenoid is a configuration in which a conductor is arranged in such a way that it forms various coils. And through these coils, current used to pass, and because of that current, we observe that there is some magnetic field. And when we try to observe the magnetic field, that how it actually looks, what we can do is we can sprinkle some iron fillings around it. So when we sprinkle that iron fillings around it, we see that the iron fillings arrange themselves according to the magnetic field originating from that bar magnet or from that solenoid. So you
Mhm.
can actually see that how they look.
Mhm.
Whereas at the corners of the poles, you can see the intensity of the field is very high. That's why more particles of the iron fillings are accumulated near the corners
Mhm.
of the bar magnet. So we'll talk about these things in detail. Before that, You must have seen this. What
Yeah.
do we call it?
The Northern Lights?
Northern Lights. Do you have any idea why we see such lights?
Mm, not really.
So we are going to learn that how these lights actually uh, originates and how do we observe this in only some part of the world, not throughout the world. There are few
Yeah.
countries only where the northern lights are visible, whereas in the
Mm.
rest of the world there is no such things. So we are
We
going to
were able
talk about this.
to see it though.
What?
We were able to see it like a little bit. A couple of months ago, or when it happened, I think it was no, it was a year ago, last summer. And
In
there's this,
California?
yeah, where we were able to see it. Although our cousins in Seattle could see it, but we could also see it from a certain point.
That's nice. But uh, do you actually saw it on a regular basis or it was just a first time?
No, no, no. That was our first time. It's not a common thing.
Yeah, that's what I'm saying. So
Yeah.
we do see here it in India as well, like in some part of Ladakh. But again,
Mm.
that is something which we witnessed like the first time last year also. So that is not a common thing here also. So what makes it common and why we are not observing it throughout the world? We are going to talk about that also. That is also something which is due to the important phenomena of magnetism only. So we'll talk about that as
Mm.
well. Before that, we need to understand that magnetic field is something which originates due to the motion of the charge. So when charges are in motion, so that thing is something which can be observed inside a conductor because we cannot see moving charge in open space. It do require some material medium, and that material medium for the charge to move is conductor. And that conductor is sometimes, or you can say the most of the times, refers to as wire. So
Mm-hmm.
whenever we observe that there is a wire and current is flowing through it, or you can say precisely charge is moving across the wire or conductor, we observe magnetic field. So if we want to find out the direction of magnetic field due to that current carrying conductor, we can use this rule, right hand grip rule. What you have to do is you have to grip that current carrying wire. This is our conductor, or you can say this is current carrying wire. This wire, in whichever direction it is carrying current, you need to put your thumb in that direction, and in whatever way your fingers curl, or in whatever direction your fingers curl, that direction will give us the direction of magnetic field.
Mm-hmm.
Like how can we actually see it? Just look at it here. So suppose this is my wire and it is carrying current in this direction. So if I try to hold that wire and in such a way that the thumb is in direction of current. So if you look at the direction in which fingers skull like this, so what you can observe, the fingers is going to get into the plane this way, and from here it is coming out of the plane. Like this is something which is representing into the plane, and that into the plane is represented by cross. That is something which is representing out of the plane. Like what I want to say here is whenever there is a current carrying conductor, that current carrying conductor may has direction of magnetic field different in different planes. What do we mean by this? Simply mean that on one side it is might be going into the plane like the field, and other side it is might be coming out of the plane. So if the wire is carrying current in this way, so we can say that it must be originating from one part and terminating into another part. One more thing about this current carrying wire is whatever type of magnetic field they create, they generally forms a closed loop like that. So it must be coming out from here and going into here. So they generally forms a closed loop like this. This is a wire carrying a current. So current must be going, the magnetic field must be going this way. So here we can say the direction of magnetic field around that current carrying wire is something which is anti-clockwise. So we will be using these terms again and again in this unit, like clockwise and anti-clockwise, because magnetic field is something which forms closed loops.
Mm.
So that is something we need to understand. So what does this rule says? If a current carrying conductor is held in a right hand, again that is important. Direction
Mm.
can only be find out when you're carrying that current carrying conductor in right hand. If you are putting it in left hand, then direction will be wrong. So held it with the right hand with the thumb indicating the direction of flow of current. Again, we have to put our thumb in such a way that it represents the flow of current. Then the curled finger around it forming the grip indicate the direction of associated magnetic field lines. So this is how the direction of field lines are generally given, and we do talk about this in detail. We have another rule to do the same to find the same direction of field, that is Ampere's screw rule. So whenever you have to find the direction, what you can do is just put a screw in the direction of current. Like suppose this is a wire and you are seeing the current is going this way. So what you can do is just put a screw and in whichever direction you'll rotate the screw. There will be two things. Like for example, if you uh, rotate it in clockwise direction.
Mm.
If you rotate the screw in clockwise direction, what would happen? It will go inside.
Yeah.
But if you rotate in anti-clockwise direction, what would happen?
Then it'll come out.
It will come out. Or you can say the screw will move outside.
Mm.
So the motion of the screw is something which is representing the direction of current. But the way with which we are rotating it is actually representing the direction of field line. So this is another way to look at the magnetic field line due to a current carrying conductor. And we are going to use these two rules in order to find out current, in order to find out magnetic field in different situations. Different situations as in through different conductors that we will talk about the field line. So this is we will be again looking at some questions during the class. So the question says if the translational advancement of the screw directs in the direction of flow of current in a conductor, then rotational motion of the screw directs in the direction of which magnetic field. Like for
Mm.
example, again it is simply asking us to relate that second law which is used to give the direction of magnetic field, which is Ampere's screw
Mm.
rule. So in whichever direction current is going, you just put a screw in that direction. And if you rotate it like in clockwise or in anti-clockwise direction, it will come out or it will go in. So that rotation, which will be there, it will decide the direction of magnetic field. So that is something which is very important. Like you can use these things to determine the direction of field, like whatever field is there. Like for example, in this diagram also, if current is going this
Mm.
way, just like in the conductor, so whenever you see the magnetic field, so magnetic field will be different in different regions. Like I can assume this is my one such region and this is my second such region. So in the first region, if you look at it, so what you will observe is that from first region, the current, the magnetic field is coming out of it. So whenever we are saying magnetic field is coming out of it, we will use this sign of dot. And in the second region, we can see that magnetic field is going inside, so it will be like cross. So this is how the field actually goes. So this is the direction of magnetic field. So this is something which is very important, and we are going to use it again and again to determine the direction of field lines. So remember this. Is it
Mm-hmm.
clear?
Yeah.
So that is the question, and the answer is magnetic field. And vice versa, this statement is also valid. If you have given the direction of magnetic field, you can give us the direction of current. So direction of magnetic field is completely related with the direction of current flowing in the circuit. So that is something which is completely relatable, and this thing can be explained using both the rules which we looked. Next is, if a straight current carrying conductor is held in a right hand with the thumb indicating the direction of flow of current, then the curled fingers around it forming the grip indicates the direction of associated magnetic field. Is what? Which rule is this?
Um, B, Ampere's right hand grip rule.
Yeah. So now let us come to the thing how a scientist or a person actually witnessed magnetic field due to that current carrying conductor thing. So in order to understand it, we need to go to the Hans Christian Oersted class. So as I told you in the first lecture also that he was a professor by profession, and he was taking a lecture in his class, and he was performing an experiment. In that experiment, what
Uh,
happened is,
1 second. The internet's cutting out. Let me just connect to my hotspot.
all right,
Okay. Is it better?
uh, I guess you should turn off your video so that it will more focus on audio
Okay.
and be focused.
Yeah.
So while doing experiments with the students in the class, what he found that by mistake around the circuit only he put a magnetic compass.
Mhm.
Before this, no one has any idea that a current carrying conductor can produce magnetic field. This was completely shocking and completely new thing for this professor also, that why this thing happened. What he observed is, like suppose this is a circuit and this circuit has some switch. When the switch was open, the compass was placed this way and it shows no deflection. But the moment we
Mhm.
close the switch, the Christian Oersted observed that the compass needle moved. Not much, it moved slightly. And as we know that whenever there is motion, there must be some force responsible for it. So from
Mhm.
that, we can say observation only, we came to a new kind of force which is called magnetic force. And that magnetic force is something which is originated due to motion of charged particle. So this was, you can
Mhm.
say, the building block of this particular unit, that how this whole thing came. And as I told you in the very first class also, like almost 50 to 60% discoveries here in physics also are accidental. But
Mhm.
what makes them discovered? The curiosity of the scientist and the behavior of asking why this thing is happening. So that question why is something which has changed the universe, or you can say the earth completely. Today By using the application of magnetic field, we have so many things around us, like literally a lot of things around us. Whatever batteries you are observing in your electronic devices are generally runs because of this magnetism thing only. We are able to recharge them, we are able to use them again and again, is generally because of electronic devices. Then if I talk about the more application part, so whatever braking system we have in metros and in bullet trains is also something which is related to the magnetism only. We do use magnetic braking system in whatever high speeding trains or metros we have. Similarly, we have this important discovery few years ago, which is of transformer. So that transformer is also something which is there due to that magnetism thing only. If we don't have magnetism, we don't have understanding of magnetism and magnetic effect of current, we won't be having these things around us. Just remember this thing, all electronic devices are there because of that phenomena of magnetism only. If we don't have magnetism, we won't be using these things. We won't be able to interact the way we are doing right now. Everything is there because of magnetism part only. We'll understand it through application part a little more in upcoming classes, but in today's class, we are actually going to learn about magnetic field, how it does originate, and what effect it creates around its surrounding. How can we
Mhm.
calculate it? What is the magnitude of magnetic field? And what force is there because of the magnetic field when a charged particle is placed in it? So we're going to talk about these things in today's class. Again, remember the experiment. At to be precise, it was not an experiment. It was just an observation, and all these things happened like a whole new unit, or you can say the branch of physics we came across when we got to this accidental discovery. Let's
Mhm.
move ahead. So, what is the SI unit of magnetic field? It is Weber. You need
Mhm.
to remember it. Oh, sorry, not Weber. It is Tesla.
Oh.
Not after the name of Nikola Tesla. Remember this.
Mhm.
You know one thing that Nikola Tesla has in his mind, like what he actually wants to give this world. He wants to give this world wireless electricity.
Mhm. Oh wow.
This was his vision.
Mhm.
Like we somehow able to distribute wireless electricity through whatever space we want. But all his, you can say, discoveries and theories and whatever he did in order to get that wireless electricity, it just vanished overnight. He did a lot of
Mhm.
research on this, but all of his discoveries got vanished and no one has no idea where it went. But if his vision was become true and we are living that reality, living that in reality, it would be a very, you can say, useful thing. It will be again little bit cheap also. The whole world can use electricity, which is like you can say the free of cost. There were
Mhm.
so many things. There were so you can say so many different factors as well. Like if this was have become reality, then most of the companies who are actually selling wires, actually making conductors, would shut. And that is something which should not be they wanted. So don't know what happened that time. I was not there, so I can't say what actually happened. But yes, his he has that vision of wireless electricity, and in future there might be someone who came and this make this thing reality for sure,
Mhm.
because it is possible. This is what I believe as well. So in future,
Mm,
we might have some, you can say the brain, genius brain, will come to the party and just make this thing reality.
mhm,
Remember the unit? Magnetic field unit is Tesla.
mhm.
Also, it is SI unit of magnetic field, whereas Gauss is the CGS unit of electric field. Remember this.
What is
Sometimes in question, what is what?
CGS?
Basically, see, there were different systems in which we measure different units. These
Mhm.
systems are SI system, we call it CGS system, and we
Oh,
also have FPS system.
mhm.
SI system is which is accepted by the world, which is standard, which is
Okay.
common throughout the world. CGS and FPS systems are those like this is which is adopted by European countries.
Mhm.
Like F is representing foot, P is representing pound, S is representing second. Whereas in
Oh,
CGS system, F is representing centimeters, G is representing grams, S is representing again seconds. So
mm,
all the fundamental quantities which can be represented by different set of units will contribute towards the new system.
mhm,
What's important we have here is that SI system is something which is very common, and every time we are solving any numerical, that numerical should be solved in SI units only. So
mhm.
remember this. So Tesla
What
is
is
the SI unit of magnetic field, where Gauss is the what is what?
oh, no, no,
I'm not able to hear you.
oh, hear me now?
It's cracking a lot. I think you should rejoin it.
Mhm. Hear me now?
It's cracking a lot. I think you should rejoin.
Okay, I'll do that. Am I audible now, sir?
Yeah, it's
Okay.
much better now.
Okay.
So Tesla is the SI unit of magnetic field. Gauss is the SI unit of CGS unit of magnetic field. Whereas if we talk about Weber, it is a unit of magnetic flux. We'll talk about that also, that what is magnetic flux and
Mhm,
how we are going to use it.
mhm.
Now, this is a very important conversion and you need to learn it. One Gauss is nothing but 10 to the power minus 5 Tesla. Again, Gauss
Mhm,
is the CGS unit of magnetic field, Tesla is the SI unit of magnetic field.
mhm.
Now, where do we actually use Gauss? That should be the question. So Gauss is something which is used to represent or express the magnetic field of Earth. So whenever we are measuring magnetic field of Earth, it is represented in Gauss, and Earth's magnetic field is nothing but one Gauss, you can say. So you can see it is not that much in number, but it is enough. This is of enough strength that it can protect us from the harmful solar flares. It can protect us from all the harmful solar flares that actually comes from sun.
Mm-hmm.
Now, this is interesting. Let me show you how exactly these things happen. Like what is solar flare and where do we actually observing it? Just give me a second. Let me show you something.
It's like a beautiful display of lights in the sky. These are some auroras that were spotted in the sky over central Alaska. We can also see auroras from space. This is what an aurora looks like from the International Space Station. The name of an aurora changes depending on its location. If you're in the northern hemisphere, it is called Aurora Borealis, or Northern Lights.
So basically what happens here is whenever we are looking at these northern lights, these are nothing but the Earth's way of protecting us from solar flares that are actually coming from sun. So you
Mm-hmm.
can assume it this way that on sun, what happens is there are lots of volcanic eruptions going on continuously. And sometimes these eruptions are so strong that you can say like hundreds of kilometers long eruptions are there. And because of those eruptions, there are some solar flares which comes to the earth. And when these solar flares comes to the earth, Earth's magnetic field protect us from those solar flares, and the effect which we observe is nothing but northern lights. So that's why we observe northern lights in
And if you're in the southern hemisphere,
evening.
then it is called Aurora Australis, or Southern Lights. So, what causes these beautiful displays of lights anyway? The sun? That's right. Right. Even though auroras are best seen at night, these colorful displays are caused by spacecraft have captured amazing auroras on Jupiter and Saturn.
So we can say that magnetic field is not something which is responsible for attraction and repulsion. The magnetic field which Earth possesses It is actually responsible for the existence of Earth. If it is not here, what we will be looking at is that most of the solar flares coming on Earth will striking the Earth and it will cause inhabitable zone here on Earth. But the atmosphere and the magnetic field and also the magnitude of magnetic field which is there for Earth, it also helps in that way. Because if there is more magnetic field that Earth could produce than 10 to the power minus 5 Tesla, then again it will be more difficult for us to live here. There will be some, you can say, factors which are going to change and it will completely change the way we live today. So that is how all these things work.
Mhm.
Again, these are the some order of magnitudes of magnetic field in different physical situations that we need to understand. When we are looking at surface of a neutron star, the magnitude of magnetic field is 10 to the power 8, which is very huge.
Mhm.
Very huge means you cannot, you can say, withstand that magnitude of magnetic field. It's very huge.
Mhm.
Whatever type of magnetic field that we use in laboratory to perform certain experiment, it is something you can say 1 Tesla. This is
Mhm.
the maximum magnetic field which can human generates and use. And after that, we are not capable of using and generating, and we don't even need to.
Mhm.
Then near a bar magnet, it is 10 to the power minus 2 Tesla. On Earth's surface, 10 to the power minus 5 Tesla.
Mhm.
Human nerve fiber, like inside humans, there is also a small magnetic field which is like 10 to the power minus 10.
Mhm.
And interstellar space, where there is no interaction, there is 10 to the power minus 12. So everywhere around us, there exists a magnetic field and we can witness it, we can saw it. Now, the most important law, Biot-Savart law, which actually give us the magnitude of magnetic force which originates due to all this. So whatever magnetic field is there, it is capable of producing some or imparting some magnetic force. That magnetic force is something which is given by Biot-Savart law. So in order to understand it, let us consider an infinite current carrying conductor
Mhm.
like that. And we are assuming that it is carrying some current I. Again, it is infinite in length, so we have no idea about its length. So we are wishing to calculate the magnetic field due to this wire at this point P. Remember this at point P. Now, in physics or in any other thing, what we actually does is like if we don't have the actual or proper length of the conductor, we will choose a element. We will choose an element, and that element is something which is called current carrying element. Like if there is a wire which is infinite in length and we cannot calculate the magnetic field due to it, so what we does is we try to find out the magnetic field due to any current carrying element which is present in it. So when we add up all these current carrying element, it will form that wire.
Mhm.
So what we can do here is we can assume that we have a current carrying element, let's say this, and this current carrying element has length dx. As we don't
Mhm.
know the length of the wire completely, so we will assume a current carrying element which is having some length dx. Now, this dx, the length of the wire, will also carrying some current. So we can
Mhm.
write that this element should be IDL or IDX. Sometimes we'll be using IDL or sometimes we'll be using IDX. So this is current carrying element we have. Also,
Mhm.
through this current carrying element, we will observe that this element is a certain distance away from that point. So we will name that distance as r. And to be precise, it should be r vector. And sometimes it is also represented by r position vector. R is sometimes also represented as position vector. So that is also you need to understand. Now,
Mhm.
this current carrying element also has some direction. This current carrying element also has some direction, and its direction is given by tangent to the wire. So at the point where the current carrying element is, we just draw a tangent like this, and this tangent will give us the direction of current carrying element
Mm-hmm.
like this, IDL. Also, you can see that there is an angle between the position vector and the current carrying element, which can be represented as theta. Remember this? This is position vector,
Mm-hmm.
which is representing the distance between the current carrying element and the point P at which we are wishing to calculate the magnetic field. And this ideal is current carrying element. So the angle between both of them is something theta, we can assume. Now, according to Biot-Savart law, that magnetic field, which is represented by B vector, will be there for the whole wire. But magnetic field due to this wire can be represented by B. But if we want to find out the magnetic field due to that element, so we will write dB because of
Mm-hmm.
current carrying element. So that magnetic field dB, now that is important, that dB is something which is directly proportional to that current carrying element ideal. That dB is inversely proportional to the distance of square between the point and the current carrying element. And that magnetic field is something which is directly proportional to the sine of angle between the theta, sine of angle between the current carrying element and position vector. So when we
Mm-hmm.
comprise or add all three equations, we'll get that magnetic field due to this current carrying element is directly proportional to IDL sine theta by R square. So again, this is important that you need to remember. We are going to use this formula a lot.
Mm-hmm.
So the dV is directly proportional to IDL sine theta by R square. Now, when we remove this proportionality, we found that dV is something which is equals to mu naught by 4 pi times IDL sine theta by R square. Now, there must be a question that comes to your mind that what is this mu naught? So, mu naught is permeability.
Mm-hmm.
Permeability is a factor which defines the
Really
medium.
the pass through.
Yeah, that how much that medium will allow that electricity to pass through that medium. So that is something which is a property of the medium. Different mediums has different values of permeability, and we do go and look into it. So remember this thing, unit of magnetic field is again Tesla and CGS unit is Gauss.
Mm-hmm.
And remember the formula as well. Once again, how can we find out the direction of this magnetic field? What we have to do is we have to keep our thumb in the direction of current, and in whichever way our fingers are curled, it will give us the direction of magnetic field. So at point P, if I keep my thumb this way, I can say that here fingers will be going into the plane at point P.
Yeah.
So it is represented by cross. So cross will give us the direction of magnetic field. Remember this. This is
Mm-hmm.
very important, and we are going to use this again and again.
Mm-hmm.
So this was the point at which we found all these field. The next question we have is which law of electricity is Biot-Savart law of magnetism analogous to? So here what we have seen is that in electrostatics there was a law which is giving us the magnitude of electric field, And here we have a law which gives us the magnitude of magnetic field
Mhm.
in magnetism. So in magnetism, we just saw it is Biot-Savart law. So that Biot-Savart are the two people who worked on it and find out the magnitude of magnetic field. Whereas in electrostatics, it is Coulomb's law.
Yeah.
We saw in the previous unit. So these two laws are completely analogous to each other, and we are going to see that how they are analogous to each other.
Mhm.
First of all, they both are long range forces. Means if there is a lot of distance between the ends of the conductor as well as you can say the charges, they will be there. They do
Mm.
exist. And next, they follow principle of superposition. Principle of superposition means if you have to find the net force or the net field, just add all the fields.
Mhm.
How? Vectorially, we have to add them. We have to add them vectorially in such a way, considering angle between them. Because these are vector quantities, and whenever we are solving them, we have to consider whatever angle is there between them. We have to use that also in order to find out the net force or net
Mhm.
field. These are the differences between Biot-Savart law and Coulomb's law, and you can look at it this way. It is
Mhm.
electrostatic field which is produced by a scalar source, and that scalar source is charge. And here, magnetic field is produced by vector source. That vector source is current carrying element, which is ideal.
Mhm.
The direction of field is along the position vector in electrostatic force, but here the direction of field is perpendicular to the plane containing position vector and current element. So whatever plane we have, that field is something which is perpendicular to position vector and current carrying element.
Mhm.
There is no angle dependence, but here there is an angle dependence. As we can see, it is directly proportional to sine theta. So these are the differences between Coulomb's law and Biot-Savart law.
Mhm.
Tesla is a unit of what?
Um, Magnetic field.
Hmm. Now there is another thing, mu naught, epsilon naught, and c. So we know what is epsilon naught, we know what is mu naught as of now, but what is c? It is speed of light.
Mhm.
So speed of light is something which is related to permeability and permittivity by this relation.
Mhm.
Remember this relation. From here only we got speed of light as 3 into 10 to the power 8 meters per second. From this
Mhm.
relation only. So again, that is also something which is important. Next, according to Biot-Savart law, the magnitude of magnetic field is directly proportional to what? We just saw it.
Mm. To the current.
Only current.
Um.
This was the relation. So here you can see it is directly proportional to current. Here you can see it is directly proportional to element, length element, and it is inversely proportional to distance of square between the curve
Mhm.
point and the wire. So current, yes, it is correct. Length of the element, yes, it is correct. Square of the distance, no, it is inversely proportional to it. So it is false. Both A and B. The correct option will be
D.
D, both A and B. So what is the magnitude of magnetic field? What we can say? Look at here. So we just saw that dB is something which is mu naught by 4 pi IDL sine theta by r square, right?
Mhm.
Now, what you can do is you can multiply both sides with r and r. Multiply and divide the right hand side
Mhm.
with r, and we'll get mu naught by 4 pi r cube.
Yeah.
Now, this is important. I can be written there and we can write dl cross r. Now,
Mm-hmm.
this is something which we have already learned in grade 11 physics, like this
Mm-hmm.
cross product thing. This dl cross r is nothing but cross product. It is not normal product, which we used to do in maths.
Mm-hmm.
This is a cross product, and this is something which is done by a complete different procedure. If I went to explain you this only, it will take a class, like a complete class.
Yeah.
So I'll suggest you that you just go and check it out that how we can solve this cross product thing. Whenever we do cross product, this sine theta just went into it. So that
Mm-hmm.
sine theta also went into it. So by looking at this question, which option is the correct answer?
B.
Yes. So as I told you, magnetic field due to current carrying wire on the line. Line means if point P lies on the line. Just look at here. So we saw that dV is nothing but mu naught by 4 pi I dl cross r by r cube. If you look at here, the distance between the point and the wire for this particular situation is going to be what?
Mm.
What was that distance is supposed to be? This r between what?
Yeah.
Between wire and the point. But here the point lies on the wire itself. What is the distance between the current carrying element and the point?
Um.
It is going to be zero. And if it is going to be zero, the magnetic field because of that element on the current carrying conductor itself is going to be zero. So what we can say
Mm-hmm.
is in order to have the magnetic field due to a current carrying wire, the point must lie away from the wire, not on the wire.
Mm-hmm.
If it lies on the wire or the conductor, there will be no magnetic field due to one conductor on itself. So remember this thing. So if there is a wire, the magnetic field is always supposed to be around it, not onto it. So this is again important that you need to remember.
Mm-hmm.
Now, one more thing. You must have seen that whenever two wires are placed in such a way, they are not placed like this. They are always placed like this,
Mm-hmm.
like cross.
Yeah.
Why do we actually need to cross them? Any idea?
Mm. No, I don't know.
It is because whenever there are two parallel wires carrying current are placed parallel to each other this way, their natural tendency is that they will push them away. Like
Mm-hmm.
they will push them away. What happens due to this is that wire might be become far from each other, and this will make it difficult for us to like place them together and hold them together and to make that circuit work. So in order to avoid that thing, we just tie them like this. That's the way we tie our hairs, like just cross them.
Mm-hmm.
So that is something is the reason that why we have that crossed wire always, not the parallel or straight wires.
Mm-hmm.
Next thing we have is what is the magnetic field due to a current carrying circular loop at the center. Now, just remember these things whenever we are talking about magnetic field due to a current carrying different conductors, whether it is circular, whether it is straight or whatever it is. We can use some different and some direct formulas in order to have that field. So what I can assume is that there is some current I which is flowing in clockwise direction. this current carrying loop must be uniform and it must have some radius. I can assume that radius is r.
Mm-hmm.
So what we can see here is that the magnetic field due to the current carrying wire, it must be represented by vector P
Mm-hmm.
like this, and it is equals to mu naught times current by 2r. That is the magnetic field due to a current carrying element at its center.
Mm-hmm.
So you can see that the magnetic field due to current carrying loop at the center depends upon current as well as radius.
Mm-hmm.
It depends directly on the current and it depends inversely on the radius.
Mm-hmm.
So remember the formula again, everything remains same, unit and all. But yeah, the formula is something which should be used in order to solve the numericals. Next we have is magnetic field due to current carrying conducting finite long wire. Again, this is going to be very interesting, basically the formula. So what we have assumed is that there is a wire which is carrying current I in the upward direction, and there is a point P which is supposed to be here, which is making different angles with the ends of the conductor. So I assumed it is making alpha with this one end A, and it is making beta with another end B of the wire. So here, what we can see is that the magnetic field due to this current carrying wire at that point P is nothing but mu naught times I by 2 pi A. Now, what is this A? This A is the distance between the wire and the point.
Mm-hmm. Mm.
This times sine of alpha plus sine of beta. So, this is the relation for magnetic field due to a finite wire. Again, what are alpha and beta? Alpha and beta are the angles which this point suspend on the ends of the conductor. What is A? A is the distance between the wire and the point P. What is I? I is the magnitude of current. So
Mm-hmm.
on these factors, it depends.
Mm-hmm.
Next we have is what is the magnetic field due to infinite wire at point P. Now assume this thing. Whenever there is an infinite wire, do we able to find out this angle like alpha and beta? Can we
Mm.
find out that angle?
Yeah.
So what should be alpha and beta in these cases?
Mm.
Because we simply have to substitute the value of alpha and beta and we get the value of magnetic field. Remember this, whenever there are two things which are like infinite in length, so the angle is supposed to be 90 degree on both the sides.
Mm-hmm.
Like this line will try to meet its end, but it will never meet its ends. So we can say that the angle given by the point P or subtended by the point P on the wire should be 90 degree each.
Mm-hmm.
So if we substitute the value of 90 degree in the formula, in this formula, mu naught I by 2 pi A times sine alpha plus sine beta. What is sine 90?
Um, Sine 90 is 1. So 1
Hmm.
plus
So that
1.
is going to be the
Uh-huh.
magnetic field due to this infinite length wire.
Mm-hmm.
Remember this, and we can use it as a direct relation. Sometimes they will ask you what is the magnetic field due to this infinite wire. They will give you the current value of current and the distance between the wire and the point. What you have to do is just apply this relation directly.
Mm-hmm.
Again, what is A? A is distance between wire and point P.
Mhm.
Now, for semi-infinite wire, what we have to do is, again, we have to find out the value of sine alpha and sine beta. For semi-infinite wire, one angle is going to be 90 degree, but what about other angle? It is going to be 0 degree. So magnitude of magnetic field is going to be mu naught I by 4 pi A into sine 90 plus sine 0. So what we are going to have in place of sine 90 and sine 0? Sine 90 is 1, sine 0 is 0. So we'll be getting magnetic field as mu naught I by 4 pi A.
Mhm.
Again, this is like more technical and you'll be solving more numericals on this. Then only you'll be able to get the field and other things. So that is something which is important and you need to look into it.
Mhm.
Next, which one of the following graph shows the variation of magnetic induction B? Again, this is a new term. Sometimes in place of magnetic field, we do use term magnetic induction. But the symbol is something which is same, which is always B. So the question
Mhm.
says which graph shows the variation of magnetic field with the distance r along a long wire carrying a current. So that distance r is something which we have seen in the formula as A. So if
Mhm.
you look at the formula, how it is supposed to look like what is the formula of magnetic field according to Biot-Savart law? Mu naught by 4 pi IDL sine theta by r square.
Mhm.
So can I say that magnetic field is inversely proportional to r square?
Yeah.
So what kind of graph we can actually observe it from this equation?
Um.
Let me give you the hint. This
Mhm.
graph actually represent the proportionality that
Oh.
B is proportional to R. This graph actually gives us that the B is inversely proportional to R.
Uh-huh.
This graph shows us magnetic field is inversely proportional to R square. And this
Oh.
graph shows that magnetic field is directly proportional to R square.
And
So
it's
C
C.
is the correct option, which
Mhm.
represents this situation. So remember all the other graphs as well. Like they
Okay.
might be asked somewhere.
Mhm.
Now, can we find the field due to this configuration at point O? Yes, we can. What we can do is we can consider these wires, these sides as four different wires, and all the wire, because of every wire, there will be a field at the center. So this
Mhm.
is supposed to be the square.
Mhm.
So what is the angle subtended by the point center to central point at the ends of the wire? Can you tell me?
Mm.
What are the angles? Like
Mm.
what this angle is?
Um.
It is
Like.
very simple. It is 45, 45.
Oh. Yeah.
Like a square diagonals intersect each other at 90
Yeah.
degree.
Mhm.
But what we are doing, we are actually dividing these two angles. So we got 45 and 45.
Mhm.
So when we solve magnetic field due to this one such wire, like AB wire, let's say,
Mhm.
I'm assuming this to be the AB points. So if I try to calculate the magnetic field due to this AB wire only, we'll get mu naught I by 4 pi A. What is A? A is the distance between point and wire.
Mhm.
Into what? Sine alpha plus sine beta.
Mhm.
So what is the value of A here? That is something we have to find first.
Mhm.
This whole length is L. So half
Yeah.
length is going to be L by 2.
Yeah.
So can I say my A would be L by 2?
Mm-hmm.
Also, sine alpha is something which is sine 45, and sine beta is also something sine 45.
Mm-hmm.
What is the value of sine 45? Tell me.
Um, 1/√2.
Hmm. Did you remember it or you just saw it somewhere?
No, I have a like unit circle graph, so we had to like memorize that in school when we did trigonometry.
All
But I wasn't
right.
sure minus 1/√2 or 1/√2. But yeah.
So is it going to be the answer? And we
Yeah.
can say magnetic field due to that one such wire would be root 2 times mu naught I by pi L. But this
Mm-hmm.
is because of one such wire. But we have the whole square and all the wires are identical. So what we can do is just multiply it by 4. So the
Mm-hmm.
answer which should be there, it is going to be 4 root 2 mu naught I by pi L. That is the answer because of this situation.
Mm-hmm.
Clear? Is this question clear?
Yeah.
Next we have is Ampere's circuital law. So this Ampere's circuital law actually relates the magnetic flux and the current carrying element. So the flux and the magnetic flux is something which is represented by closed loop integration of V dot dl, and it is nothing but mu naught times the current passing through it. So
Mm-hmm.
how can we explain it? How can we actually understand it? So whenever there is a wire carrying some current I, in order to find the magnetic field because of the wire, what we can do is we can assume a circular loop around it. That circular loop must be closed.
Mm-hmm.
And whatever wires, number of wires are passing through these circular loop, that the sum of all the currents, mu naught times the I total, is equals to V dot dl. Again, this dot is dot product. It is not simple multiplication, it is different thing.
Mm-hmm.
So the Ampere circuital law says that the line integral of V dot dl takes over the entire closed path of the induction, that is field, in a given perpendicular plane is equals to mu naught times the total current enclosed in the closed path. Again, it
Mm-hmm.
is very technical thing, like understanding this. Just remember, this law is something which is used to find out the magnetic field for various different configurations for which
Mm-hmm.
we cannot find using Biot-Savart law. Just remember it this way. So for those configurations for which we cannot apply Biot-Savart law, we'll actually apply as Ampere circuital law.
Okay.
So use Ampere circuital law to find out B dot dl. So see, mu B dot dl is something. Now there are two values of current. What does this dot represent? What I told you about this dot?
Um. Um.
Think of it. What does this dot represent?
Um. I'm thinking. Like.
So is there
the-
any other symbol also apart from dot?
Yeah. The. Uh. Don't know what you call that in the beginning. But does it represent like the product
It
between like
represent like
years?
the direction of current or sometimes the direction of magnetic field. So dot means it is going out of the plane. Like here you can assume that there must be a loop, and this loop has two wires, and these two wires supposed to carry current in the outward direction, I1 and I2, like this. So this is what it represents,
Mhm.
dot. And cross is something which represents into the plane. So here, both the wires are carrying current, and they are carrying current in such a way that it is coming out of the plane.
Mhm.
So whenever we are going to calculate it, what we have to do is whatever wires is lying inside the loop will only contributes towards this B dot dl. So it would be I1 only, not I2. But if I2 wire is something which is also there inside the loop,
Mhm.
it is going to be I1 plus I2.
Mhm. Oh, okay.
Yeah, that is what you have to understand. Also, there is another case. If I have a circular loop which is carrying current in this way, like there are two wires, one is carrying current in upward direction, other is going into the plane. So B
Mhm.
dot dl is something which is equals to mu naught times I1 minus I2 this time.
Mhm.
So depending upon the values also, we will describe it this way.
Mhm.
Use Ampere's Circuital law to find B dot dl. Again, it is going to be what? B dot dl times mu naught I, and we
2.
write minus 2 minus I2 because here
Wow.
the direction is reversed.
Oh, yeah. Mhm.
But we won't include this I1, remember, because it is outside.
Yeah.
If the integral of B dot dl around any closed loop or Amperian loop is 0, then net current through the Amperian loop must be 0, net charge must be 0, B in that region it should be 0. Ampere law doesn't hold good for in this case. So this is obviously very wrong because Ampere law is something which is there everywhere, so it is cannot be wrong. Magnetic
Mhm.
field is 0 in that region. That is also not possible because if there is current carrying element, there must be some magnetic field. Net
Mhm.
charge must be 0. Again, that is also not a case because if net charge is 0, then we can say that there is no current. So correct
Mhm.
answer is the net current through the Amperian loop. It is something which is 0. Like you can assume it this way that there are two wires. One is carrying current in upward direction, other is carrying current in downward direction. And the magnitude of both the wires, current carrying wire is same. Then we can say that the B dot dl is something which is 0.
Okay.
So what is that case? That
Okay.
net current is something which is 0. Then only it is possible.
Mhm.
Now again, this is a question and I guess you should try it out. Another configuration called solenoid. The solenoid is a coil when number of coils are arranged parallelly to each other
Mhm.
and they are connected well, like this. So you can
Mhm.
see that if they are carrying a current, it must be going like that.
Like in a
Or you
notebook,
can,
like
yeah,
spiral notebook. Yeah.
like a spiral thing. But that spiral is not, that particular figure is not something we call spiral, it is called helical.
Oh, okay.
So technically it is helical, and the spiral which we just use in day-to-day life is something which is like this.
Mhm. Yeah.
So that is something which is spiral, that is something which is helical. So it is a
Mhm.
number of coils are arranged in such a way, then only we can see it. So we are going to calculate the current or the magnetic field due to that current carrying wire. You can also assume it to be a spring because
Mhm.
spring is something which is conducting in nature. So
Mhm.
a conducting spring which is carrying a current is something which is known as solenoid. So we do calculate magnetic field due to this solenoid, and we do see it in day-to-day life as well. Like in
Mhm.
every device which actually works of charging something, like
Mhm.
your phone charger, your laptop charger, or whatever charger you are using, every charging instrument has solenoid in it.
Mm-hmm.
because it is something which converts magnetic field into electricity, or you can say the current.
Mm-hmm.
So again, that is something which is being there in like every device, every instrument which carries charging.